SwayamPrabha. Digital India. Educated India.
Dear learners, greetings from IIT Guwahati. We are in the MOOCs course Power Plant System Engineering, module number 2, that is Vapor Power System part 3. In today's lecture, our main focus would be on steam condenser. So, under this heading, we will try to discuss the following components, that is condensate and feed power systems. Then we will talk about two types of condenser, like one is direct contact type, other is the surface condensers. So, both the condensers will be discussed exhaustively in this lecture. But before you enter into those condenser details, let us try to understand the first basic need, what we call as condensate and feed water systems. So, if you look at this particular diagram or thermal circuits, which consists of boiler, turbine, condenser and pump. In fact, this thermal circuit we discussed in one of the earlier lectures, that is beginning of module 2. So, for this thermal circuit, our main target that we are going into details of this condenser unit. So, why do you require these condenser units? That is mainly because if you recall this TS diagram, that is temperature entropy diagrams for based on Rankine cycle of steam power systems, what we see is that the turbine inlet condition is at state 1 and this steam expands in the turbine and finally, it comes to the state 2. So, after expansion of the steam in the turbine, it reaches to the state 2. Now, while reaching its state 2, the steam condition is either a superheated regions or in the liquid vapor region. So, but this steam has to release the heat in a unit what is called as condensers. Now, the another essential requirement is that more and more you can expand in the turbine, it is then the output from the turbine will be higher, and that is possible if we operate the condenser at lowest possible pressure. So, what does this mean? That during the expansion process from 1 to 2, one can stop this expansion process at any intermediate points on this diagram, but the lowest possible point will yield maximum turbine output. So, in other words, if a condenser is operated at the lower pressure, then work output or enthalpy difference, that is between H1 and H2 will be increasing. So, that is the reasons we require this condenser to operate at very low pressures. Second requirement of the condenser in the steam power plant is that this from the output from the condenser is again fed to the pump and it gives necessary feed water to the boiler. So, that is the reason we also require a feed pump that takes the water from this outlet of the condenser, or we call this as a condensate, and then it is given to the pump for a higher pressure. The pressure in the water reaches to the boiler pressures. So, this is the main requirement. Another important point here is that once the outlet from the condenser is usually called as condensate, but feed water is the another term that this condenser has to also supply required amount of feed water to the pump. So, that is what two things are coupled together when dealing with the condensers, but however, we are going to treat them separately. So, in this lecture we will mainly focus on the primary part, that is condensers. In the subsequent lecture we will talk about feed water systems. What does this mean for feed water systems? Because the feed water can come from variety ends, one can come from the turbine end, one can get from the condenser end. So, that part will be discussed in the separate lecture. But our main role in this lecture is that we are going to deal with the important component, that is condenser. Its main role is to condensate the exhaust from the turbine to recover high quality of feed water for reuse in the cycle. As you can see, at state 3, the condensate or the high quality feed water gets circulated in the cycle. The most important part is that turbine work is higher when the condenser is operated at lower pressure, and mostly we say that if you can operate the condenser pressure mostly in the vacuum, then we can maximize the enthalpy output. So, some of the additional requirement for the condenser is that by lowering the back pressure in the condenser by few unit, it gives additional advantage of increasing work output from the turbine, plant efficiency. Of course, it gives reduction in the steam flow. So, and thermodynamically it is also important to use the lowest cooling water that are available for use. For example, to get this heat out from the turbine exhaust, what we require is that we require the cooling water to get circulated in the condenser. So, in other words, it means that when you take this inlet temperature of the cooling water, it should be at par with the water availability at that location where the condenser is installed. The main purpose of feed water is to improve this cycle efficiency by heating the condensate to 200 to 250 degree centigrades. So, in the later point of these things we will say that when you take out the condensate, I mean we do not really bring back to atmospheric temperature, rather that condensate we try to leave them at around 200 to 250 degree centigrades, so that at the entry to the boiler the boiler load will come down. If you allow the condensate or feed water at this 200 to 250 degree centigrades, and then supply water before returning to the steam generator. Then these feed waters are mainly two types, one is direct closed type and open type. We will talk later in the next lecture. But our main target is that we have to very basic point is that we have to look into the steam condenser unit, and this steam condenser unit should operate much below the atmospheric pressures. For example, we should at least 40 degree centigrades, that is normal temperature, and at that 40 degree centigrades the saturation pressure or condenser pressure we normally call as the saturation pressure at 40 degree centigrade, we call this as a condenser pressure, and that is typically 0.074 bar. So, this is the standard way that all the steam turbine operate, and one must understand is that your atmospheric pressure is much above this condenser pressure. So, that is the reason we say that always vacuum condition is maintained in the condenser. Then let us see the types of condenser. There are two types of condenser. One is direct contact type, other is surface condenser. So, what we see in the direct condenser type, here both the cooling water and the condensate, they are allowed to mix, whereas in a surface condenser these two fluids are treated as two different entities. For example, normally the exhaust from the turbine is either superheated steam or it is like the liquid vapor region or mixed region steam with desirable quality of about 80 to 90%. So, in a direct condenser what we do is that we do not restrict the mixing of stream. What it means is that if you look at this figure, the exhaust from the turbine is at state 2 and the water that comes enters into the or circulating water that enters to the condenser is at state 5 and both are allowed to mix in the condenser and the mixer is leaves at state 3. So, this is what we call as a direct contact type thing. That means, two fluids that enters into the condenser, they mix and the resultant stream comes out as a condensate. But whereas in a surface condenser type, which normally most of the modern power plant use, they use a cell and tube type heat exchanger. What you see is that you have a turbine exhaust here. So, the turbine exhaust comes in the steam dome which is in these locations and this is normally enters to the cell side. That means, this dome is connected to the cell and entire cell is occupied with this turbine exhaust. But what we do is that we do not allow the circulating water to mix with the steam. So, in that case what should you do? That we have some inlet water temperature segment which enters and then they continuously move in this condenser in a multiple times. So, we call this as a single pass, 2 pass, 3 pass or any number of passes. So, that the entire heat which is available at the exhaust of the steam from the turbine gets trapped by this circulating water. That means, at the end our outlet temperature of the circulate reaches to a maximum value. So, that is the reason we ensure that the water passes through multiple tube sheets and we call them as a 2 pass, 3 pass, 4 pass like that. So, in that sense we can use the maximum utilization of heat while steam releases heat to the cooling water. So, the surface condenser are essentially the cell and tube type of heat exchanger in which the primary heat transfer mechanisms are condensing the saturated stream outside the tubes and the forced convection heating of the circulating water inside the tubes. So, the majority of the power plant use the surface condenser because effectiveness of heat transfer becomes higher. Now, let us try to understand both these steam condensers separately. So, first let us start with a direct contact type steam condenser. In the one of the variant, the direct contact type condenser, we call this as a spray condenser. So, the spray condenser uses a dry cooling tower and it takes all kind of it is a cooling tower that is nothing but it is a water reservoir that stores water at normal room temperature or atmospheric temperatures and it supplies the water to the condenser unit. Now, during its supply water is sprayed inside the condenser from the top and at the same time we also allow the turbine exhaust to pass through this medium and through this process we have a steam, we have a water and the mixing of both steam and water takes place and during this at the end of these things most of the steam that releases the heat to this water and the resultant part which is collected as state 3 and called as condensate and then it is fed to the feed pump. Now, here at point 3 there are two segments, one goes at state 4, other again return back to the cooling tower at state 5. So, as you can see here from we are now after the turbine exists we are now at state point 2 and here the state at the state point 2 it is a thermodynamic state where the quality of the steam is around 85 to 90%. So, from 2 to 3 that happens in a condenser. So, through this process of heat release, the vapor becomes liquid at that saturation pressure and temperature, and we reach at the state 3, that is condensate, which is collected at the from the outlet of the condenser unit. Now, at 3, some of these things that water has to be pumped into this. So, basically one part goes to state 4, other part we can leave it to state 5. State 5 means somewhere here, that means we can release that to further lower temperature, because this is about 40 degree centigrade and state 5 is normally close to water temperature which is available for use in the cooling tower around 15 to 20 degree centigrades. So, this is further lower temperatures. So, in other words, that means one unit that is so and that same water is again enters into the condensing unit. Now, here most important thing that we need to find out is the mass flow of water requirement for a given quantity of steam. So, that part we want to calculate, and that is called as circulating water to steam flow rate, ratio of circulating water to the steam flow rate. And this from this thing what we can understand is that we can frame mass balance equation and energy balance equations for this spray type condensers, and here we can see that M2 dot, which is the exhaust from the turbine, is equal to M24 dot, which normally leaves. Second thing, at if you very particular for the condenser, we can see that M3 dot is equal to M2 dot plus M25, this is mass balance, and energy balance for this condenser can be written as M2 dot H2 plus M dot 5 H5 is equal to M dot 3 H3. Now, from these two equations we can find a ratio, and what is called as most important ratio, that is ratio of circulating water, circulating cooling water to the steam flow, which means that for a given unit of steam flow what is the requirement of cooling water, and this is the most vital part for the, and that decides the load of the condensers, and based on that load of the condenser all other parameters like how many number of tubes, what is the number of pass required, how many passes we need to do, then further what is the diameter of this outer diameter and inner diameter of the tube, all these things can be designed. The next important part or segment for direct contact condenser is a barometric condensers. So, normally if you look at the previous spray type condenser, they use pump. Now, in order to replace this pump, what we initially people have thought of putting a tailpipe of certain height, and this tailpipe tries to replace the requirement for the pump. So, necessary pressure difference is achieved by using a tailpipe, and this tailpipe is sufficiently high, and we take the advantage of barometric height which is h to take care about the pressure difference, and this pressure differential, that is rho g h, is nothing but atmospheric pressure minus condenser pressure difference, plus it has to also take care the frictional pressure drop in this pipe, and that frictional pressure drop is related to the friction factor, height and diameter of the pipe, velocity of the flow in the pipe. So, all these things we know, so that we can calculate what is the pressure differential based on this height can be designed, and this is one part. Second thing is that here this cooling tower arrangement is like a baffles, that means there are multiple number of baffles. So, the water is continuously gets in contact with the exhaust of the turbine. Another important aspect of this thing is that non-condensables. So, for example, water which are condensed, they goes out of this through this tailpipe, and whatever non-condensables, they have to taken back through a steam jet air ejector system. So, these are what we call as unwanted parts for the as far as the condenser requirement is concerned. And the role of this tailpipe of this mixture is to compress the mixture to atmospheric pressure in the hot well by virtue of static head, and thus it replaces the need of the pump. This is one aspect what we call as barometric condenser, and here also both exhaust from the turbine and the cooling water they are allowed to mix. Now, another design of jet pipe condenser, another design of this barometric condenser is preferred, because many a times we also require very long pipe, because the pipe of constant length and diameter we require long pipes. So, that variations can be regulated by keeping a diffuser type design in the tailpipe. So, essentially the tailpipe is replaced with a diffuser type designs that involves a throat which is a minimum area sections, and side by side this geometry of the shape is a kind of a diffuser, where the water gets through this process we get desired pressure difference across this diffuser. So, here also the cooling water and turbine exhaust they are allowed to mix, and in a cascade arrangement, so that proper mixing is possible. So, we require various cascades to enhance the heat transfer from the turbine exhaust to the cooling water. So, here also there are provisions that we must use the steam jet air ejector to remove the unwanted condensable non-condensable gases. Now, if you just compare both barometric and jet type condensers, they are almost similar designs, but very basic difference is that the tailpipe requirement of barometric condenser is close to not less than 10 meters. So, that length gets reduced if you go for a jet type of condenser. Now, we will move on to next type of condenser, which are called as surface condensers. So, I mentioned earlier the surface condensers are cell and tube type heat exchangers, in which the primary heat transfer mechanisms are condensing the saturated steam on the outside of the tubes and forced convection heating of the circulated water inside the tube. Here we see that there is a cell. The cell means it contains the steam dome, and entire unit we have the steam, but the water enters into the condenser through multiple tube seats, and through this process the condensate, that means the heat transfer takes place. So, steam gets condenses, and the condensate is collected in the hot well which is below the cell. So, in this process we get much more or enhanced heat transfer, or the mechanism of giving high quality circulating water to the boiler. So, that is the advantage of the surface condensers. So, there are some standard informations for steam condensers, that is when the steam condensates its volume decreases. So, that means we have very few tubes, smaller passes to drain the water into the hot well, and this hot well receives the condensate that acts as a reservoir, and it is with a capacity equal to the total condensate flow rate at a particular time. And for these surface condensers, normally copper tubes of with diameter 1 to 3 millimeter is used, and length 1 to 3 meter is used, and their length is typically 25 meter, which are preferred for a large scale power plants. Number of passes determines the size and effectiveness of condenser. So, which means that enhanced heat transfer is possible if you allow this steam to move inside the condenser in multiple times, and that what we call it as a pass. So, as you can see, for a given water velocity, if you try to link the how much pressure drop takes place, which you can see that two things, that means for a given flow rate of inlet velocity of water, which is at this location, let us say it is 2 meter per second, and if you go for 2 pass type of system, that means you allow the water to pass in the to circulate 2 times, then we have a larger pressure drop. So, that means for 2 pass systems we have a larger pressure drop. Second thing is that when you increase the number of passes, we will land up having higher pressure drop. That means higher pressure drop means more effectiveness of the condenser, and through this process the condenser size also will gets reduced. In other words, this means single pass condenser will have a larger size than that of a 2 pass condenser. A single pass condenser with same number of tube and size with same water velocity requires twice the water flow. So, it results half of the temperature rise and have lower condenser pressures. So, that is the reasons in many cases most power plants prefer single pass condenser when this requirement of thermal pollution is the essential. But in terms of water requirement and pumping requirement, we generally prefer 2 pass condensers, because the single pass condensers involves higher cost. So, a balanced approach in number of passes essentially decides the size and cost of the condenser. The another important aspect of this surface condenser we are now going to see call as they are called as deaeration, deaerator. So, what it means is that in a steam and vapor power cycles, it is important to remove non-condensable gases that gets accumulated in the systems. We have been keeping on emphasizing the fact that there are non-condensables gases that comes out, that is that which are non-avoidable at the turbine exhaust. So, those non-condensable gases has to be relieved or released. And what are they? These non-condensable gases, they are nothing but the mostly air that leaks from the atmosphere at various portion of the cycle, number 1. Number 2, there could be decomposition of water, that is hydrogen and oxygens, and they are mostly predominant in the nuclear power plants. So, these things has to be removed in the condenser, because why they have to remove? Because the presence of those gases adds partial pressures, and this partial pressure through this, and when they have their own partial pressures, so that way the total pressure of the system increases. This first demerit of these non-condensable gases. Second demerit is that the blanket of heat transfer surfaces, that means these non-condensable gases creates a kind of insulation blanket on the heat transfer surfaces, and thereby it decreases the overall condensing heat transfer coefficients. So, that is the reasons these non-condensable gases has to be removed. Another thing is that there are if there are chemical presence in the non-condensable gases, then they can add to corrosion. For example, presence of oxygen add corrosion to heat transfer surfaces. When there is a corrosion, the overall heat transfer coefficient drops, and then the purpose of the condenser load also performance of the condenser will drop down. So, many a times most of the fossil power plant requires the guaranteed oxygen concentration should be less than 0.005 centimeter cube per liter. So, essentially the role of oxygen in a condenser has to be is very significant, because it adds corrosion, it drops overall heat transfer coefficients in passively, and they have their own partial pressures. To suppress all of the things, we require a additional unit that is called deaerator, and that is normally used in the surface condensers. Then another study that we are going to do, because most of the steam power systems they use surface condensers. So, we will try to focus our attentions some of the important parameters, and mainly we call this as a heat transfer analysis. And this heat transfer analysis requires the knowledge of the condensing steam, how it takes place. So, for example, if you see here, we have two streams. One is exhaust from the turbine that enters through the steam dome into the cell. Other is the cooling water that enters at the inlet and comes in the outlet. And since the turbine exhaust, which is close to the saturated vapor steam, and inside the condenser, its role is, that means it is condenses, that means there is no drop, no change in the temperature, rather there is a release of latent heat of vaporization for the steam. So, this heat is being taken away by this water. So, if you have inlet temperature 1, so it is when it heat takes away, its temperature at state 2 increases. So, thermodynamically or you can say through heat transfer, if you can say the temperature versus heat transfer path length, either you take in terms of area or length, then we have two temperature differences. One is delta Ti at the inlet. So, it is essentially the arrangement of a counter flow in which one fluid is condensing, other fluid is temperature is increasing. So, one temperature is delta Ti at the inlet, other temperature is delta To at the outlet, and this delta To is normally for the condenser viewpoint, we call this as a, mainly surface condensers, we call this as a terminal temperature difference. So, this parameter is very vital, because that adds to the cost, sizing and performance of the condenser. So, more and more this temperature difference is, that means if you have a very higher temperature, that means your at the outlet temperature, that means performance of the condenser is very good. So, that is the reason the terminal temperature difference is kept as low as possible, and typical number is close to 3 degree centigrades. That means, from the difference between the steam and the outlet temperature of the circulating water should be in the range of 3 degree centigrades. Second important aspect is that at a given temperature difference at the inlet, larger TTD results large LMTD, smaller area, and there is, so that there is an increase in the water flow, and because this water temperature rise is reduced. Smaller TTD will result in larger condenser area with reduced water flow and higher exit temperatures. And because of this smaller size, that means our design is not perfect. So, we call this as a oversized condensers, and it will invite higher capital cost. So, in the condenser design, this TTD is very much vital in designing various components of the condensers. Now, to design the various component of condensers, there are some standard calculations, and that is supported by heat transfer modeling, and these standards involve the Heat Exchange Institute standards for steam surface condensers. So, the equation that is simplified, that is we call this as a heat load on the condenser, is based on overall heat transfer coefficient U multiplied by area, that is the surface area, and this area is nothing but your n into pi d0 into L. D0 is the outer diameter of the tube, length is the length of the condenser, n is the number of tubes that are being used. And this delta Tm is the logarithmic mean temperature difference for the condensers, that depends on the inlet temperature difference and the outlet temperature difference, that is TTD. This is calculated by this parameter delta Tm. Now, what is not known to us is that u. Now, this u is a function of various parameters, and this standard the proposal or the given by this heat exchange standard says that overall heat transfer coefficients can depend on various factors. What are the factors? First factor is depends on the outer diameter. Second factor is circulating water inlet temperature. Third factor is tube material and gauge. Fourth factor is cleanliness, and this is proportional to the square root of velocity. So, u is equal to C1, C2, C3, C4 square root of V. So, while if you are interested to design a steam condensers, then we have to look into all these parameters, and then accordingly we can calculate the overall heat transfer coefficients. But however, in our course this value will be mostly given for the condenser calculations. Then moving further, the next part that we require, that how much water is being how much heat is being carried out by the water, and that is required with the condenser load, that is Q, and we also require the other important parameter, what is the mass flow rate of the circulating water, that is nothing but the temperature differential that we are supposed to achieve, that is T2 minus T1, and from this we also have the condenser load Q. Another parameter that which is also required here is that pressure drop in the condenser, that is delta P, rho Gs, this also can be calculated. And typically the inlet temperature of water is kept between 2.1 to 2.5 meter per second. So, these two parameters is also very vital in the designing of a surface condenser. Now, finally, this is the overall picture that how surface condenser designs details are taken into account, but however, other important aspects which is very vital and we are not following in this lecture is that the kind of cooling that happens in the condensers, and this is what we call as a film wise condensation in horizontal tubes. So, we have seen that there are tubes in which the water flows inside, and if you take the cross section of this tube where water is gets circulated in the tubes at any particular instant, if you see there are water temperature Tw, and there is another dome which is called as saturation temperature of water, because we have outside we have steam and inside we have water. So, there is a layer and we call this as a condensate film, and this there is a thickness which is delta, which is nothing which engulfs about the diameter of the tube in which water is there. So, this particular concept we call this as a film wise condensation, that is different part altogether, in which that also comes in the design of steam condensers. Another kind of knowledge that we require in the design of the condenser is heat transfer mechanisms, which means conduction through tube walls, forced convection inside the tube at varying temperatures, and then also you need to evaluate heat transfer coefficients as various parts of the condensers, that is cell and tube, inner and outer surface, all these things are required. And both of the things will give you the heat load on the condenser, and Additionally, this heat load must be removed from the by the feed water, and that is the reason condensate and feed water are taken together, and all non condensables has to be taken out from the condenser unit by a component called as a steam jet air ejector. So, considering all these things together, we can say that heat transfer mechanisms in a condenser is quite complex, but what we have presented here is a very simple way, so that numerical problems can be attempted. So, with this we conclude, but however, before you close this lecture, let us try to understand some of the numerical problems which are part of this lecture. So, the first problem is on surface condenser design and its calculations. So, the problem statement goes like this: the surface condenser receives 240 tons of hour of steam at 40 degree centigrade with 88% quality. The cooling water enters at 30 degree centigrade and leaves at 38 degree centigrade. The pressure inside the condenser is 0.078 bar. Velocity of circulating water is 1.6 meter per second. The tubes of the condenser have 25 mm outer diameter and thickness 1.25 mm. We need to find out what is the rate of flow of cooling water, air leakage into the condenser, and length and diameter of the tubes. So, essentially we can draw the schematic what we have shown earlier is that we have tubes of that in which water enters and water leaves. The tubes have outer diameter 25 mm, thickness is 1.25 mm. Now, water inlet temperature is 32 degree centigrade, outlet temperature is 38 degree centigrade. Steam enters at 240 tons per hour, and here quality of the steam is 88%, and this condenser pressure is 0.078 bar. Overall heat transfer coefficient, that means condensation takes place on the surface. Overall heat transfer coefficients for this tube is U0, which is 2560 watt per meter square Kelvin. So, this is the problem. So, we need to require two diagrams. First diagrams, let us see how that expansion process takes place in the turbine and where you stand. So, if you say TS diagram, there is a dome, so the state of the that enters in the condenser at 2 and it leaves at 3, and this temperature is 40 degree centigrade. Second part is that we also need to look at this, how the condensation happens across this heat transfer length. So, if you say temperature versus path length, that is A0 or L in this direction, then steam condenses in this manner. So, this is a counter flow heat exchanger and cooling water temperature increases, and this is delta T O or that is TTD, and this is delta T I. So, from the data that is given, we say this temperature is 32 degree centigrades, this is 38 degree centigrades, and condensation takes place at 40 degree centigrade, that is T saturated. Okay. So, these three diagrams will give you most of the informations. So, having drawn these diagrams, we will be now able to solve this particular problem. So, let us see the first thing, what is x 2 is given as 88%, that is 0.88. We also have data at 40 degree centigrades. We can calculate what is the value of HFG, that is saturated temperature steam table. So, HFG value can be noted as 2407 kilojoule per kg, and also we have then we can say what is the condenser load, that is H 2 minus H 3 is equal to x times x 2 times HFG. So, both the parameters we know, then we will have 2118.2 kilojoule per kg. Once we know, then we can perform energy balance for cooling water and condensed steam, that is mass of the steam m dot s, that is condenser load, that is H 2 minus H 3, that is total condenser load, and that is taken by mass of this cooling water into CPW Tc2 minus Tc1. So, we have all the data, Tc1 32 degree centigrades, Tc2 38 degree centigrade, CPW 4.187 kilojoule per kg Kelvin, that is for water, and mass of the steam, that is m dot s, which is 240 tons per hour, that is 240 into 1000 by 3600. So, this value is 66.66 kg per second. So, by inserting this value, we get 66.66 into 2118.2 is equal to m dot c, which is unknown, CPW 4.187, Tc2 minus Tc1 38 minus 32. So, this will give you m dot c, that is equal to rate of mass flow of cooling water, that is part A is solved as 5620.5 kg per second. Now, for the second part, rate of air leakage into the condenser. So, the rate of air leakage into the condenser, if you take this total condenser volume is V, and that total volume can be calculated. Is mass of the steam into specific volume of the steam. Now, here we require specific volume of the steam, that is V 2 is equal to V f plus x times V f g. Now, at 40 degree centigrade, we can say, we can calculate what is V 2, 0.001008 meter cube per kg, x is, that is x 2 is 0.88, and VFG is equal to 19.544 meter cube per kg. So, this data we get from the steam table. So, from this we can calculate what is V 2 is equal to 17.2 meter cube per kg. So, we also have mass of the steam, that is m dot s already calculated 66.66 kg per second. Then we can use the equations, ideal gas equations PAR, because you need to find out what is the air leakage, into V is equal to m dot air, which is we need to find out, into R air into T. Now, next question is that what is this PAR? Now, this condenser operates at pressure, total pressure, which consists of saturated pressure plus air pressure, which is already existing in this condenser. So, that value is 0.078 bar, and this P saturated pressure at 40 degree centigrade is 0.07375 bar. So, from this we can calculate PAR as 0.00425 bar, or so this value is 0.425 kilonewton per meter square. We have PAR. Now, RAR is equal to 0.287 kilojoule per kg Kelvin. Temperature 40 degree centigrades, which equals to 313 Kelvin. Volume already calculated, that is m dot s into V 2. So, putting this number, what we will get is 0.425 into 66.66 into 17.2 is equal to m dot AR, which needs to be calculated 0.287, that is RAR into 313. So, this will give you rate of air leakage as 5.42 kg per second. So, this solves the second problem part. The third part, that means we need to calculate the length and number of tubes. So, for that reasons we have to bring the overall heat transfer coefficient U A0 into delta Tm. Now, this delta Tm is equal to delta Ti minus delta Te divided by ln delta Ti by delta Te, that is equal to 8 minus 2 by ln 8 by 2. So, this number is 4.33 degree centigrades. U is given 2560 watt per meter square Kelvin. Q already calculated as 60 m dot s into H2 minus H3, that is 66.66 into 2118.2. Then we can get A0 is equal to 66.66 into 2118.2 divided by U, that is 2.56 into 4.33. So, area you can calculate right now is 12738 meter square. Now, this area we know this area is equal to n times pi d0 into L. So, what we do not know is n, length is given, no, n is not known, L is also not known. To go do this, then we can link this mass flow rate m dot c is equal to of mass flow rate of cooling water, that is equal to n times pi by 4 d I square into rho times V w. V w is the water velocity, that is given as 1.6 meter per second. Density of water 1000 kg per meter cube, and m dot c already evaluated as 5620.5 kg per second. D I is given as 25 d, that is the outer diameter, minus twice t, that is 25 minus 2.5. So, d I is 22.5 mm. So, in this equation all are known. So, this will give number of tubes is equal to 5620.5 into 4 divided by or you can say write like this, pi by 4 into 0.0225 square into 1000 into 1.6. So, number of tubes, that is n is equal to 8834. So, number of tubes answer we got. Now, what is not known is length. So, that things we can now calculate. L is equal to A0 times n pi d0. A0 is already calculated 12738, n is 8834 into pi into d0, that is already given 25 mm, 0.025. So, this will give you L is equal to 18.35 meter. So, this entire problem discusses about how you need to go for a condenser design. The second problem is a very simple one. So, this emphasizes the important aspect, the ratio of circulating water to steam flow rate. So, circulating water is m dot 5 in a direct contact type spray condenser, and this steam rate is m dot 2. So, here what we need to look at here in this diagram. So, we have one condition at state 5, second condition at state 3, and third condition is at state 2. Okay. So, for a spray condenser, if you calculate the mass and energy balance, so you can recall our equations, that is m dot 3 is equal to m dot 2 plus m dot 5. So, that is mass balance, and m dot 3 H3 is equal to m dot 2 H2 plus m dot 5 H5, that is energy balance. So, these two equations will give you a ratio, that is we call this as m dot 5 by m dot 2, that is H 2 minus H 3 divided by H 3 minus H 5. Okay. So, now our main job is that for with the given data we need to find out. So, first thing that condenser operates at 0.07 bar. So, at 0.07 bar we can take saturated pressure table, steam table, that is we can say HFG is equal to 2407 kilojoule per kg, T saturated is equal to 40 degree centigrade, and then HF at that 40 degree centigrade is 162.2 kilojoule per kg. So, that means we can say H 2 is equal to HF plus X times HFG. HF is 162.2 plus X is 0.9, which is 90% into 162.2. So, we get H 2, that is condenser exit from the turbine, that is 2328.5 kilojoule per kg. So, we know H 2, what is H 3? Not H 3, which is at this point it is equal to HF at 40 degree centigrade. Already we have calculated 162.2 kilojoule per kg. Next thing H 5. H 5 is at condition here. So, cooling water is at 15 degree centigrade. So, we say H 5 is equal to HF at 15 degree centigrade. So, this value also can be calculated, obtained from the steam table, and that number is 65.26 kilojoule per kg. Now, after inserting this value, we can say get m dot 5 divided by m dot 2 is equal to 2328.5 minus 162.2 divided by 162.2 minus 65.26. So, this ratio becomes now 21.83, which means the circulating water has to be 22 times higher than the steam flow rate, which is quite high for a steam power systems. So, this gives you the important concepts and numerical problems based on this lecture today. With this, I conclude this session. Thank you for your attention.